In this section, you might notice that in your book, this is called section 7.1, and the actual title is Basic Approaches to Integration. But in all the MyMathLab stuff, it's going to be section 8.1. So there's just a difference in version between MyMathLab and the textbook that some of you purchased. The chapter in the section itself is exactly the same. All of the examples are the same. All of the instruction is the same. It just has a different chapter number. So you might want to grab your textbook right now, whether if it's digital, then it's definitely 8.1. But if you have a hard copy of the textbook, then it might be 7.1 or 8.1, and so you can check that out right now and then just follow along with that same corresponding chapter here for the next several weeks. Okay, so with that out of the way, we are going to be talking about some basic ways to approach integration. None of these are supposed to be new approaches to integration. The idea is to use stuff that you already know how to do in order to integrate. So let me give you a couple of things from algebra that you should be familiar with. The first one is polynomial long division. The second is a process from algebra called completing the square. And the third is multiplying by a conjugate. So again, none of these three strategies or techniques is from calculus. Each one is something that was taught whenever you took algebra. But you may not remember some of these techniques, so it may be a good time to go back and review. And I'll give an example of each technique. But what we're going to do is we're going to utilize them in order to integrate some pretty complicated looking things. So aside from the algebra, here are the integration techniques that we're going to be looking at in this section. So we'll have a list of them. So one integration technique that you should be familiar with is substitution. And so a U substitution is something that we learned from Calc 1, and so we should still be able to apply that now. The book also refers to something called subtle substitution, and that just means that in some cases you may need to rewrite the given expression a little bit before the substitution becomes a little bit more obvious. So that's one technique we will use. Another technique is the technique of splitting up fractions. So it's sort of like the opposite of getting a common denominator. Okay, so rather than taking two fractions, getting a common denominator and bringing them together into one fraction, we'll split them apart. Sometimes that makes it easier to integrate. Another technique, again, is the division of rational functions. And this is where our polynomial long division technique will come into play. So if you have two expressions that are divided, that creates a rational function. And if you actually do the long division and divide them out to find out the quotient and the remainder, then you can integrate each of those pieces a little bit more easily sometimes than you can the rational function itself. The next one is going back to something I mentioned before, completing the square. So sometimes we have something that is in quadratic form, and if we complete the square, we create this binomial squared term. So in other words, we're putting a quadratic in a form that looks similar to this. And one of the reasons that we would want to do that is that creating this squared term can sometimes lead to a more easy integration. And then the last one is sometimes you can take a fraction and multiply it by 1. Obviously here we don't really mean the number 1, but we mean something that is equivalent to 1, like x plus 3 over x plus 3. So sometimes multiplying can simplify a denominator or just make things easier. So these are all things to keep in mind and ideas to use when you're integrating. So the idea of this section is give you a bunch of different problems, and you don't know what strategy to use, but you try something and you're able to integrate in the long run. So what I'd like to do now in the video is I'd like to go through an example of polynomial long division, an example of completing the square, an example of multiplying by a conjugate. So if that's something that you are not interested in seeing, then I would suggest that you go ahead and skip ahead to the next video where I'll actually start doing some integration and applying some of these techniques listed. But if you need the algebra review, go ahead and stay with me and we'll do an example of each of these. Okay, so polynomial long division. So if I take, for example, some polynomial expression, which I'm going to make one up, this quadratic expression 3x squared minus 2x plus 1, I could potentially divide it by some other polynomial. In this case, I've chosen x plus 4. So you might see the original problem written in this way, where you've got the top divided by the bottom. And again, what we want to do is we want to actually divide this in so that we come up with some sort of quotient and then some sort of remainder to represent the division of these two polynomial expressions. There are actually lots of ways to do this. You might want to pause right here, try to do it on your own, and then we'll skip ahead to the quotient and the remainder and you can see if you remember. So just do a little quick check of yourself. But the other thing that I want to remind you of in this case is that the degree of the numerator must be greater than or equal to the degree of the denominator in order to perform this algebraic process. So in other words, if my x squared term was on the bottom and my linear x term was on the top, that would not be something that we could divide. So our degree on the top has to be either the same as or larger than the degree on the bottom. Okay, again, some of you may want to pause here and see if you can actually remember how to divide this out. We'll give the answer and then we'll go through the process. Alright, when we divide, the quotient that we should get is 3x minus 14, and the remainder that we should get is 97 over x plus 4. So if you remembered how to do that, great job. You can skip through the explanation and maybe look at the next piece, which will be completing the square. And if not, stick with me, we'll go through the process. So what I'll do for long division is I'll first look at dividing the first two terms. Can x divide into 3x squared? Yes, it can. It goes in 3x times. So then what I'll do is I'll take that 3x and I'll distribute it through x plus 4 and bring it down. So that'll give me 3x squared plus 12x. From here, what happens is that we subtract. Now you always want to remember that you're subtracting both terms. So this negative sign really gets distributed here. 3x squared minus 3x squared gives us 0. Negative 2x minus 12x gives us negative 14x. And then you might want to just bring down the other term there so that you don't lose it. Let's repeat all of that again. So again, I want to see if x can go into negative 14x, and it goes in negative 14 times. Let's once again multiply, distribute through, bring it down here, and subtract. Negative 14x minus, whoops, I just realized that in my notes I wrote that as a 96, and it's actually a 56. So I'm guessing that this remainder is probably not correct. I just had a little multiplication mistake that I didn't notice until just now. Sorry about that, we'll fix that. Let's subtract. Okay, so negative 14x minus a negative 14x is 0. 1 minus a negative 56 is a 57. At this point, x doesn't divide into 57, so we get our remainder there, 57 out of x plus 4, or divided by x plus 4. Here we have quotient and remainder. So that's polynomial long division. Let's take a look at the process of completing the square. So when we're completing a square, we're using expressions that are in quadratic form. For example, x squared plus 4x plus 7 is a quadratic expression. The idea is to write it once again in this form. X plus something squared, and then plus or minus something. So lots of different ways that people memorize the completing the square process. Generally what we do is we take half that middle term, and that gives us a 2. And then we add or subtract some constant in order to adjust that expression so that what we have here is precisely equal to what we have here. So let's just do a quick check in terms of what this perfect square will produce. X squared plus 2x plus another 2x plus 4. So it gives us x squared plus 4x plus 4. What we really wanted was 7, so think about what do we have to do to this 4 to get 7, and that is that we have to add 3. So the process of completing the square here leaves us with this expression. And so in the end, when we've completed the square, we've taken the quadratic that we were given, and we've rewritten it in a different but equivalent form. So again, these two have the exact same value, they're just written in a different form of a quadratic. So that's completing the square. Alright, let's move on to the last algebra technique, which is multiplying by conjugate. So a conjugate is an expression, is an expression that only differs by the sign in between. And I think this may have come up in one of our most recent videos. But for example, if I have this fraction x plus 5 over x plus the square root of 2, one thing that I might do is multiply by the conjugate of this denominator, which would be x minus the square root of 2. Whatever I do to one part of a fraction, in other words, whatever I do to the bottom of a fraction, I also have to do to the top of the fraction in order to not change its value. So this is also like multiplying by some sort of fancy 1. This expression, x minus the square root of 2 over x minus the square root of 2, is equivalent to 1, But what it will do for us is it will remove the square root from the denominator of the fraction, or rationalize that denominator.